The next talk is going to be fault injection on a modern multi-core system. It's going to be awesome, by the way. We've got some hardware here. So take it away, Sergey and Ronan. Oh, cool.
Great. Does my mic work? Can you hear me? No? Great. Thank you very much. It is very nice to be here. First times at MCH. It was a lot of fun. Thank you for coming on Sunday, hot night. We're going to talk about fault injection, and we're going to talk about modern hardware, how fault injection works, and what is fault injection. So all that, we're going to talk in a minute. Who we are. We work at Riskier. My name is Sergey. I like software, hardware, playing with things. And yeah, and with me, Ronan today.
Yeah, hi, I'm Ronan. I also work at Riskier for a number of years now. I like software stuff, hardware stuff, where they meet low-level fault injection, everything.
Okay, so before we go into what is fault injection or what is modern SOC or does it work, we'll first talk about physical attacks a tiny bit. So what are physical attacks? Imagine you have a device, you have it in your hands, you can do whatever with it. You can take it to the lab, you can hook in any hardware, you can put a scope to it, you could do anything with it. And you want something from this device. So for example, there are some secret vendor keys and you want to get them. Maybe it's illegal, not talking about legality of things. Let's say you really have to get them. Or there are user keys. Maybe you are an attacker. You are somebody evil, you stole the device, you want to get the keys out, you want to attack this user. And for these things, fault injection or physical attacks in general are quite useful. Another use case is getting firmware. These days, often maybe if you do networking, you can see that a lot of OTA updates, they're encrypted. You cannot easily just see what the update is or what kind of code is running on the device. So having the device in your hands and doing physical attacks can give you these secrets or giving you the firmware which runs on the device to do other attacks you want to do in the future. So that's why physical attacks are quite relevant to a number of different devices. There are two main types of physical attacks when we talk about it. There is, on the left, side channel analysis. This is passive attack. So we don't really affect the target that much. We try to avoid that. We want to make sure that the target operates normally, and we observe all kind of side channels. So not the output the target produces, but the data you can get, like maybe you can see the power trace, or you can see the scope data, you can see EM produced by the target, and so on. So this is one type. We're not going to talk about it. We're going to talk about fault injection, or also known as glitching. So that's the moment when you want to make sure that the target you have does not behave as it should. So you try to introduce a fault, and hopefully bypass some security features of the device. So yeah, what are the types of fault injection? When we talk about it, there are different types. There is quite a bit of literature on this, a number of presentations talking about of different possible fault injection methods. For example, clock glitching. So if you have external clock of your target, you can affect it in a way. You can affect the outputs of the target. Or voltage glitching. So you can disturb the voltage and observe the effects. Also, another type is electromagnetic fault injection. So you introduce a pulse into the target, and you try to affect it that way. Other types could be laser or even temperature in some cases. And what do we achieve by introducing glitches? So quite often what we see is that we can corrupt data. So instead of having, you can think of like you have some code running on the target, and there's a variable, and it has some value. And instead of having that value, if we introduce the glitch in the very right moment, we can corrupt it to another value. For example, to 0 or to FF or to dead beef, which would be quite rare, but nonetheless possible. So glitches are normally not fully random. We cannot just get any value when we glitch. It's often something quite specific. So for example, zeros are quite often. Another option, we could corrupt an instruction. So instead of executing one instruction, we execute another one. Or as a subset, we can skip an instruction. So you have some code running. At some moment, maybe you have a if statement. And if you skip this instruction, this check was not executed. And if it was security check, it might have very big effect on the security of the whole device. Just to give a bit of more intuition of why this is happening, for example, you have your device, and you introduce voltage glitching. If you have your chip, and you know that it's supposed to run at 1.8 volts. That's what your vendor tells you. In the data sheet, it will say it should be 1.8 volt, maybe 10% tolerance. But after that, device not supposed to operate in this range. So what happens if the attacker is changing the voltage of the provided to this chip for a split second? So if it happens for too long, the device likely resets. So you just disconnect and power cycle the device. But if you do it for a very short moment, you might affect the behavior of the chip. And the reason behind that is, of course, because in software we think about binary things. We think about 0 and 1 and nothing in between. In real life, there's a lot of different physics happening, and we might misread a value, a signal which is supposed to be as 1, as 0, when we introduce a glitch, or other way around. So these kind of effects are quite possible. So yeah, that kind of makes sense, and it's easy to understand that, yeah, we can affect the way the chip behaves, but of course, we cannot just know what kind of code executes where. So for example, we're on our chip, this is power trace. We just measure with a scope the power consumed by the device, and we see something like that. But it's very difficult from that map it back, even if you know the code, say, exactly there we have the if statement, which I want to skip. And this is the first problem. And the second problem, there's also quite a bit of jitter quite often on targets. So your clocks are not perfect. When it's 8 megahertz, it's never exactly 8 megahertz. It floats, temperature changes, so you will always fluctuate around. And for that reason, fault injection is never, very rarely 100% successful. So sometimes you will be more successful, sometimes less, and sometimes you need to search quite a bit of a parameter space to find this exact spot when you want to introduce the glitch. And you will have some probability, sometimes it's very high, sometimes it's not that high, to be successful introducing the glitch in this exact moment. So that's one of the problems you have always when you do fault injection. That's something you have to figure out. And yeah, we're not always fully blind when we do this. So for example, this is another example. We have a power trace, we send the command, and then we introduce the glitch in the red, and then we see the power cycle. So likely what happened, the glitch was too hard, and we caused the chip to reset. So, and we can often see it on the scope, and we know that maybe this is too much. We need to try to be more careful to affect the chip, but not to reset the chip. And this kind of information is always useful for us. So hopefully all this makes sense, and you think, yeah, you can definitely do this in the lab when you control everything, when you know the code, when you have data sheet, when you have everything you want. But does it actually work in real life? And yeah, it definitely does. There are quite a few examples when it was used. So maybe one example, what we've done in the past is glitching Bitcoin hardware wallet. So it runs a simple microcontroller. It has a STM32 chip, and we used EM fault injection. So for this device, it was open source code, so we could look at the firmware, which is always very nice. Even when you do physical attacks with hardware, it's nice to know what software does. And the weakness is that they have a single if statement, checking is pin correct, and if it's correct, allow access to the user. And for us, when we see it, we know if it can affect this if statement, we can bypass the main security feature of the device. And yeah, that was a successful attempt. You can look it up online if you're interested more in this research. So that's nice, but indeed, if you look into research which is published, like the one before, this is a STM32 simple microcontroller, which runs at 200 megahertz. There is more other research. For example, this is published at Cardis a few years ago, which studied in depth a lot of different possible effects of laser fault injection on ATmega 328P chip, which is 8-bit microcontroller from AVR, which is very simple. And this is a common situation because a lot of research focuses on simple chips, which are easy to get. So you don't want to focus on something you cannot put your hands on. You have to have it in your lab. And yeah, you rather have something simple to be able to understand what's happening. But that's why quite often it happens that a lot of people raise a question, will it actually work on modern devices? If you have a smartphone, can you glitch that? Because it runs quite quickly, has lots of cores. It is quite different from a microcontroller. And yeah, can we glitch when it's faster than 1 gigahertz? Is it even possible, or is it too fast for us to have meaningful effects on the device? And that's something we wanted to discuss in this presentation. So first of all, what's the difference between a simple microcontroller and a system on a chip, like something, a main computing unit in your smartphone? Well, the difference is one of them is very simple, another one is not so much. So there are a bunch of different features you could look at, and pretty much everywhere you can say microcontroller is just way too simple. So you have single core quite often. It is not rare to see 8-bit microcontroller. These days you can see 32-bit and more. Feature size for on the silicon is also often quite much bigger than you would have on your latest smartphones. Microcontrollers are often quite generic, so you don't have a lot of specific acceleration. Sometimes you would have crypto operations implemented, but not always. And it has very simple packaging, so it's a small chip, and everything is easy. With a system on chip, you often have a lot of cores, so it can be 4, 8 cores. Sometimes you have clusters, you have big and little cores if you talk about smartphone SoCs. And it's 64-bit most of the time. Feature size is very small, so the chips are huge. Manufacturers go a long way to make the silicon as small as possible, so it's quite different technology behind it as well. It has a lot of dedicated engines. So you have your crypto engine, which does a lot of different crypto. You maybe have AI module, which does a lot of AI acceleration and so on. So there's a lot of specialized hardware. And to make it even worse, often you have package on package. So you would have your chip, your CPU, and there is on top you have DDR. So you cannot easily access the chip. This is not the case in our example, but Ronan will talk in a minute what exactly we done our research on.
Yeah, thanks. Yeah, so Sergey has now introduced all the parts that we're interested in. What are SoCs, what system on chips, why are they interesting, what is fault injection, all of this sort of stuff. And can it be used in modern, fast processors and stuff? So that's what we decided to look at. And for this work, we decided to use this board that you see on the right, which is a Pine 64. It's a relatively modern system on chip. It's by a manufacturer called Allwinner. It's their A64 SoC. It runs above 1 gigahertz. It's multi-core. It's relatively recent. And this is basically just a single board computer. So as a Raspberry Pi, just a development board, quite cheap, quite easy to obtain. And we were able to talk publicly about this. So this fitted all the boxes for being a nice target to have a look at. So yeah, now we know what we want to glitch. How do we actually go about doing this? So this that you can see here is quite a generic EM fault, so electromagnetic fault injection setup. You can see the various parts here in the bottom left. This PCB with the wires coming and going is the target itself. The big yellow box that you can see above it is the EM probe, which is the thing that actually delivers the glitch. So it's just got a lot of capacitors and stuff inside it. It builds up a charge and then discharges it very quickly through a metal coil, which is situated right on top of the chip. You have this big table that it's all mounted on is basically just for moving the probe physically in space over the body of the chip. That's just very simple. It's just 3 motors in each of the 3 axes, just so you can control where in space you are. On the right-hand side, you can see at the bottom is an oscilloscope, which we use for debugging the setup, verifying that everything's working as expected. And the yellow thing on top of it is a spider, is basically just for controlling the EMFI probe and reading data from the target itself underneath. So that basically just says, when do we want to glitch? And it controls the rest of the hardware, which is quite dumb. But yeah, so that's one of the major things with EM fault injection. It's about where specifically. So you have the chip underneath the probe, and of course, with a modern SoC, with any SoC, different parts of it will be located in different areas on the silicon. So you might have different effects, whether you're above the CPU, above the memory, above what other components. So this allows us to control all those parameters, search through them, see where we're seeing interesting stuff. So, okay, we have a target that we can control, we can run code on it, we have our setup, everything's good. The first thing we then will do is just implement a very simple piece of code. This is just something that's running on the device, which will just have 2 variables, reading and writing from memory, one counting up, one counting down to some number that we decide. And so we use very simple things like this as a very first step, often to just get an idea for how powerful you need your glitch to be, where in space, so where above the chip it needs to be, just a very coarse-grained scan to reduce some of these parameter ranges that we're interested in. And so we run this initially for a while. You can see on the left-hand side, the ones highlighted in green, this just, as you can see, returns the up count and down count. The green ones are expected responses, meaning the glitch did not affect the device at all. So you see the 50 and the 0. The results you can see on the left, highlighted in red, are ones where we have successfully modified the code executing on the device without crashing it. So we've done a transient glitch on it. And so you can see, for example, the first one, the 51, is the up and the down. This is very likely caused by us skipping, as Sergey was talking about, skipping this decrement, the decrement of the down counter. Similarly, with the 49.0, it's skipping one of the increments of the up counter. And then you have other ones like if you know a bit of C programming, this big 4 billion number might seem familiar to you. It's the maximum value you can store in a 32-bit thing, variable. So basically this is saying that we've modified one of the decrements to not decrement by 1, but instead to decrement by 3, I think it is in this case. So it just shows we can have all sorts of varied results for what we're doing, and this sort of very simple test is a nice, easy way to just see where is good to glitch, how powerful, just to get an initial idea of the parameters that you want to use for your testing. So it might not be so easy to see here, but this is basically just a representation of the many glitching attempts we have done. The back, the darker part, is just an image of the packaging of the die itself, and we've basically just divided that whole space into whatever grid size this is. And we can see all of the green spots are where we have had no effect on the device at all, so it's just returned exactly what it should return. We didn't modify anything. The pink spots, if you can see, are not so interesting. They're different error with the setup itself rather than the device being modified. But what we're most interested in is the ones that we color red here. So all of the ones that are red we have changed the way the device is operating, but it is still operating in a normal way otherwise. So we've had a useful glitch without crashing the device. And yeah, generally what we're trying to do is change all of our parameters, be it where on the chip we are, how powerful we are, all the various things we want to control, to get the most reds, because we generally think they're the most useful ones. The device still works, but it's done something it shouldn't have done. Oh yeah, and all of this is just running at the default clock speed of the A64 sock we mentioned, which is 400 megahertz. Yeah, just to get an initial feeling for how the chip reacts. So then if we wanted to go into a bit more detail, which we did, to be able to see a bit more fine-grained effects and just to understand things better, one of the things we did is implement what you can see on the left here is just a simple function in assembly, which will take a fixed known value that we can see up here, the A5, 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 and just read it and write it to and from memory. And do nothing else. So in the case where the device is operating normally, you have not done any fault injection, it will just give you back at the end that exact same A5, A5, which is an arbitrary choice of constant. And then using the hardware setup we showed earlier, we will basically deliver our glitch at some point during this loop, which is just reading and writing that variable. So then what we want to see is can we affect, how can we affect the operation of the device in a way that's useful to us. Yes, so also, similarly to before, we can see on the left some of the results that we obtained. The normal response, as I mentioned, the green stuff on the top is just that A5, A5, A5 constant. And then in the red part below, we see some of the more interesting ones that we saw. So we said we were interested in seeing, can we have precise single bit flips on, be it the data that's being used or the instruction stream itself. These are sorted, this is a selection which is sorted on how often we saw the results. All of these top 5 ones are single bit flips away from this A5, A5 constant. So you see they're all very similar, but they differ by 1 bit in the binary. So that is saying the data that was being read or written to memory, we have been able to modify it in only 1 bit, so 1 bit precision, but the device has not seen it, so it's still useful for us. Another result that we saw quite a bit was instead of this full A5 repeated 4 times being returned, we would get just a single A5, and that is basically the way the ARM64 assembly is encoded. The instruction that loads the full 32-bit value versus the one that returns just a byte, they are also 1 single bit flip different from each other. So what we've seen there is that we can affect both the data and the instruction itself, which loads the data. And then we see also on the bottom some other different results, which are very hard to reason about because there's a lot of stuff going on the chip. It could be that it's corrupted one of the addresses to somewhere random. It could be a data corruption. There's many possible explanations, and it's hard to say given the control that we have. So yeah, that shows some of the point, the single bit flip stuff that we wanted to look at. And here what we're looking at is similar to the previous picture. It's just the results of each attempt overlaid on the chip body itself. I mentioned there's a number of different parameters we want to control: time, space, power, etc. One of the things we were interested to look at is how the operating frequency of the underlying chip affects the ability to be able to have successful glitches on it. So what we're looking at is on the top left, the current multiplier. Is basically just there's an extra step in telling the chip how fast to run. So the top left is the slowest speed, which is I think 140 megahertz roughly. And the bottom right is the fastest speed that we were looking at, which was 1.2 gigahertz. And so we can see by the number of greens, the number of reds, and yellow, which is not relevant for us, there is a very clear correlation between how fast the chip is running and how easy it is to have a noticeable effect on the chip without crashing it. So something that could be useful from a security point of view. Yeah, so that already shows two things. We can have the nice single bit flips that we were interested in, and actually, possibly counterintuitively, the faster it is, the easier to glitch it is for some. And then this just basically shows on a graph simply what we've just seen before. For each of the frequencies we were interested in, there was roughly 90,000 attempts at each frequency here. And you can see there's a clear correlation between the chip running faster and the chip being more susceptible to fault injection. So this just shows the same thing. So then one thing that you might think about is why? Why would it be that the faster you run, the more easily glitched you are, the more susceptible you are to fault injection? So this is one possible explanation. If you see at the top is a representation of a power trace or a trace of the device when it's running at a slow speed, 600 megahertz, and the same operation when it's running at a faster speed, 1.2 gigahertz. Obviously, you can see in time, and the x-axis is time. In time, the same operations are clearly much more compressed. So the way the hardware that we're using works is the amount of time it takes for the coil to discharge fully, so to deliver the glitch, that is fixed. That's a constant. So, and that's this 52 nanoseconds you see at the bottom. So you can see that as the amount of operations in that time is way higher, there's way more potential chance to affect one of them, because you're inducing the current while all this is happening. The more things that are happening, the more chance there is something can go wrong. This is a very hand-wavy explanation, but it's one that's quite easy to understand. So that's one of the explanations. And yeah, so we've seen for fault injection, we can do it. We can affect all sorts of code, sometimes security sensitive code. So naturally, you might ask, how can you defend against this? Because even with perfectly programmed software, you can still introduce faults, which can introduce bugs. So yeah, there's some stuff that you can do in the hardware itself, so bake into the silicon of the SoC. So these hardware sensors, you can do things like detect when you're operating outside of your normal voltage range that you expect. And if you see that you're outside of that, reset the chip or stop executing, so stuff like brownout detection as well. For laser fault injection that Sergey mentioned earlier, you're shining a laser onto the chip. You can also have light sensors in the silicon itself, which detect if I'm seeing too many photons, like too much light at this point in time, at this point in space, then yeah, reset, do something like that. So that's at a hardware level. At a software level, you can also follow various like programming practices, patterns to defeat, to make these sorts of attacks harder. Some of them, for example, is random delays, as Sergey mentioned. There can be jitter, there can be all sorts of changes in the timing of the program, which you as an attacker need to be able to precisely say, I want to go here. If you start introducing just random delay loops, that changes where in time the interesting operations are. So that's one. You can do redundant computations. So do the same computation twice. If you see a differing result, then that means likely there's something has gone wrong, be it fault injection, be it whatever, and then again, early out. You can do stuff like control flow integrity checking, so just making sure you are executing in the order you believe you should be executing in, and you're getting functions called, for example, from the place that you think they should be called. And then there's also some other stuff about using certain, whenever you need magic values, true, false, using ones that are hard to flip using fault injection, so hard to turn from one to the other. And yeah, so everything we've shown so far is very, in a controlled environment. We have full code execution on the development board. We have all this nice fancy equipment that's precise and expensive and everything. But then it comes to the question, so how about when you want to do that on the cheap? How about when you want to have some fun and not need expensive equipment? Can we still do this sort of stuff? And that's what Sergey is going to tell you about.
Yeah, so for the demo, we thought about bringing our setup from the lab, show you how it's done. Tiny problem with going to MCH with the equipment from the lab. There was 100% chance we're going to spill beer on it somewhere in our tent. So we didn't do that. But we still wanted to show how glitching could be done. So here's Niels, our colleague. He brought his equipment. This is Hobby's tool Pico MP. It has a similar idea. So you also have a coil. You can see the bottom. And you can introduce a glitch, also EM glitch. And we got this nice badge from the organizers, which can run a lot of different software. And we thought, and it has a lot of different chips. If you looked at the schematics, or at least at the back of the chip, there's a lot of different stuff. So we thought it might be fun to try it. And so what Niels did the first day, he got it, he wanted to try. He looked at this Pico chip, and it controls a few things, for example, the backlight of the screen. And that's a bit of a video. If it works, we can show you. Yeah, it works. So yeah, you can see the coil. In the lab, we use a nice XYZ station with a micrometer precision. Here, Niels has nanometer precision, and he can put the coil exactly in the spot to be close enough to the Pico chip. And you can see the screen here. He presses the button, he introduces the glitch and the backlight. So the chip likely resets, and yeah, it just the light goes off and on. There are also some other effects. You can see it shows restarting or some other things. So yeah, we can affect the chip. It's not very nice glitch. It's unlikely as an attacker you really wanted to come close to the user, press the button, and make sure his backlight doesn't work. But yeah, it's a something we can do here. We thought maybe there is something else, and graphic we could show on the badge is nice target for us. So we found this nice app, great to have a lot of different ones. It says it runs on FPGA, so there's also FPGA chip on the target. It's Mandelbrot. It shows you these two nice sets. You can, with a button, switch between those two. So you click the button, you have that one. You click the button again, you go back to the original screen. So these two screens you're supposed to have, and nothing else should happen. Well, you can zoom in and out, but that's it. So we started to glitch first, of course. FPGA chip is on top, a nice target. When we get close to it, it resets. We can see that the screen is just, the graphics goes back to the original position, so to this screen. So if we zoom in and out or move around and glitch the chip, it will just reset back to this. So we glitched around. What often also happens with fault injection, instead of targeting the chip itself, you often can, for example, introduce a glitch in a capacitor next to it and affect it through the voltage, introducing first EM and then causing voltage change in the capacitor. So we found that if we target this area, marked in red, we can really affect the chip and get different outputs. Then Niels looked it up in the schematics. It was very nice from organizers also to our open source everything on GitHub. So we could see that this is voltage regulator, which produces 1.2 volts, which eventually goes into the FPGA board. So that's plausible. We hit the voltage regulator, and something happens with the FPGA, with the graphics. So what did we get? This one was one of the first glitches. This is totally not what you're supposed to see. So what you're supposed to see, you remember those two, and that's the output. And the interesting thing is, we could affect the chip. We get totally different graphics on the output. The chip still runs perfectly, and these features of switching the graphics, the Mandelbrot set, and zooming in and out still works. So the chip operates perfectly. We can do operations on this and get different graphics. And there are a few others which are totally different, but also very different from what you expected to see on the screen. So you see, this is zoomed in, zoomed out, and this is zooming in big back, and it works. We could also once get this glitch, which is totally what you not expect from a recursive Mandelbrot set. Just cover the whole screen with some ASCII graphics. And finally, an interesting glitch we got this morning is this. This is totally not what you expect. We don't press any buttons. We glitched it once, and it just started to alternate between these two pictures back and forth again and again. So that's more or less what we've done being here. Some takeaways. So first of all, physical attacks. If you write software, it is quite often overpowered. You can do so many things. It's so difficult to protect. Attacker can often put much more effort into trying to break your device. Another thing which we learned, modern SOCs, they are not much less vulnerable, the hardware itself. There is still hardware attacks which apply to it. And even if you run very fast, and as we showed, sometimes it can be even easier affected. So you have smaller feature size, you have tiny transistors, you have huge frequencies which are crazy, and yeah, we can corrupt a lot of things running the device. And very important, the last point, official MCH page is susceptible to fault injection. So maybe something for the next time to improve if that's the attacker model. Thank you very much. We still have some time, so we can try to fail miserably in trying to show one of those glitches. You can see we have it here on stage. Thank you very much.
If it actually works, though.
OK. It still runs. I can maybe show you how it's supposed to work if I'm careful enough. So you have these buttons. You can zoom in, zoom out if you didn't try this app. So you can see something like this on the device. So if we try to glitch it, first I will target it's on the back. Yeah, so I can show you, for example, the backlight if I'm successful. Yeah. Oh, no. So normally it doesn't happen. This time we turned off so I glitched the Pika chip, and it's supposed to reset, and we lose the backlight and go back on. Now it's persistent, so if we're lucky, yes. So I reset now by disconnecting the wire, and it goes back in, and everything works.
And just to maybe quickly say something about the hardware, this is very similar to what we described. This is just a battery pack. This Raspberry Pi is for controlling the logic. This is the coil. It just builds up a charge in here and just discharges it very quickly through that coil right beside the chip itself. And that's how you're introducing the fault.
OK, and so the first attempt was not an awesome demo. We got the persistent glitch. Now we'll try, maybe if we're lucky, and find the spot. I'm now focusing on the regulator, trying to be very careful, moving tiny bit at a time. Ideally, it would be few micrometers.
Yes, and it's worth mentioning that in practice, when we're doing projects and stuff, we have all of this automated. So that's why we have all this fancy XY stage and all these sorts of things. if you maybe saw the glitch there, is so that we can set it once and just forget it, let it run, collect hundreds of thousands of attempts, where here we're clicking manually each time to do a glitch, so slightly less optimized.
You could see tiny effects on the screen, and this area is actually very sensitive, so we can, luckily, if we're successful enough to get actually good glitch here, but if it doesn't work in a second, that's going to be it.
Is it actually still operating?
Yeah, this area, when it shows on the half of the screen that it blinks, it's normally successful. Unfortunately, this time we didn't get it. If you want to try it out yourself when you come to us after the presentation, you can see it. That's why you should never do a demo, it never works. Thank you very much, and if you have any questions,
thank you so much. We have a little bit of time for questions, Q&A. So if you want to ask a question, there's I think there's 2 microphones. So line up behind the microphones there. So Signal Angels, do we have any questions from the internet at all? Not seeing any. So are there any kind of how are these attacks kind of used in the real world? Are there any? I mean, you mentioned about the Bitcoin wallet, right? Is that are there other examples of that you can kind of see?
Yes, it depends on the field that you're operating in, but there's many examples. So in the early 2000s, for example, when we used to have set-top boxes for getting our TV channels, you would have a smart card that you'd put in and out. One of the ways that if they detected a problem, so if you were trying to do something malicious, they would put it in a state that just sits in an infinite loop. There was devices which were publicly available, which you could basically just plug the smart card into. It would do this sort of fault injection, and it would recover the card. So it would break it out of that loop. So yeah, you can recover a dead smart card, which then you can use for piracy and other stuff. There's other examples, a lot of the attacks on more recent game consoles and stuff, like, for example, Xbox 360. I think there's something with PlayStation, utilize a lot of this fault injection stuff through various means. Yeah.
Awesome, thanks. So we have a question. Yeah, go ahead. Oh,
hello?
Yeah, a bit closer to the mic, right?
I was wondering how much something like ECC RAM could help prevent fault injection.
ECC, yeah, I mean, it can be helpful. It depends on the ECC algorithm and stuff you're using, but yes, if it's correcting single bit flips in RAM itself, then yes, it can be helpful. But also some of the stuff we're talking about is in the CPU itself, so in the instruction decoding, instruction fetching logic, all of that. So that might not be operating from DRAM itself. So it wouldn't help against that, but if you're trying to affect something in RAM, then yes, it could be helpful.
Thank you very much. Is there another question at the back there? Yeah, go ahead.
Yeah, so as we saw during the demo, there is sometimes a persistent glitch. Is there anything you can tell about what the risk is of permanently damaging the device or corrupting data, for example?
It is not that often. If you know what you're doing and you don't short all the pins, which is mostly the reason why it gets permanent damage, just with the fault injection, when you introduce, for example, in this case, EMFI, we've run the setup in the lab for millions of attempts, and there was no permanent damage, and that's quite often. So you can repeat it again and again and again, and everything works. Even here, you see, it's not really permanent. It just until the next reset, it just ended up in a weird state. So yeah, it's quite rare to damage it with the EM. If you do voltage, it's more often when you prepare the sample, you're gonna damage it, or if you do laser, you're more likely to cause the damage by the laser. So.
All right, thanks.
Thank you very much. So no more in the room. Any more from the? Oh,
Yeah.
Is that a question? No, he's just
Yes.
walking away. No. Okay. Any more from the internet? Can't really see. I think I'll take that as a no. Okay. So I think this hardware is going to be here for a little while. Yeah, this is the last talk this evening. So if you want to come up and have a look at this after the talk, I'm sure you'll be more than welcome to do so. Oh, we have a question. Great.
There are even more, actually.
I couldn't
First
see.
of all,
Okay, no
thanks
worries.
a lot for your talk. And do you have a favorite fault injection method? Like personal favorite?
Yeah, one of the reasons why I used EM is because it is quite easy. So we don't really need to do anything with the target. We just have it as it is. We don't need to decap it, so there is no chemicals involved, no polishing. We just get it as it is, and we can start glitching. So we don't need to modify power and so on. Yeah. And that's what we often use because it's the simplicity.
Okay.
But it also depends a little bit on your use case, what you're trying to do. So, for example, if you're doing laser, you can affect very specific things more easily, like in space. With voltage, for example, it's generally more an all or nothing. But yeah, as Sergey mentioned, EM is often a good one because it requires no modification, where the others both do. But yeah, different types for different desired effects.
Okay, and have you ever tried laser glitching from the backside, like with infrared lasers?
Yeah, so that's mostly what we do with lasers. So as I guess you know, you have your polysilicon layer, you have your metal layers above. We will usually always go through the silicon because to that wavelength of light, it's essentially invisible. Whereas if you were to try and come through the metal layers, the laser can't easily penetrate them. There's a lot of scattering, so it's much harder to do. It's possible in some circumstances, but usually it's backside.
Okay, thank you.
Thank you. Another question.
Hello, I have a practical question while you still have the badge on the screen. What happens if you glitch the die on the LCD controller? Have you tried?
That's the Raspberry Pi, right?
No, the LCD controller glass die in the front, on the LCD itself.
If we just try to glitch the screen itself,
Yes.
I'm pretty sure nothing will happen. We can easily do it.
You should.
Yeah, this screen, not that easily affected, but
You might have some effect if you're on the ribbon cable, though, because then you're inducing. Yeah, look, there's something.
so on this part? Okay. Let's see if we get a success here.
Okay.
There are some things, yeah, indeed.
Okay, thank you. That's what I wanted.
That's great. Yeah, another question. Yeah, sure.
So I understand that you, by mapping with this XY gantry, you can map out spatially where you can position the EMF pulse to affect instructions or data. But how do you synchronize?
Thank you.
Oh, nice.
Sorry to interrupt you.
No, that's fine.
To show for a second. You see, it still works. It shows totally what you not expect to see here. For the rest, it's, yeah. Maybe even the switching button works if I can, yeah. You can see this weirdness here.
Just a practical question. How do you, because the pulse itself is like 52 nanoseconds or something.
Yep.
How do you synchronize that temporally with, because I assume you want to affect a specific, like if there's an if sentence, you want to affect that one and not the preceding subsequent instructions. Mm-hmm. How do you synchronize that?
Yep, so that's a good question. So, I thought the slides were up there. So what we will usually do, in this case where we had complete control over the target, the code running on it, yes, this here, the line that says trigger high, that basically just sets one of the many GPIO pins, it just drives it high. So from when we saw the setup earlier, there was a box on the right that was controlling all the rest of the hardware. That will wait until it sees that trigger, and then it knows to, after a fixed amount of time, then you deliver the glitch.
Yeah.
So in this case, we can just set a GPIO, so that's easy and that's fine. In more complex targets and targets where we don't have control, we can use other signals to trigger on. So to say, from this point in time, wait. That can be reading from an eMMC. It can be some EM emanation from another component. It can be many different things. But yeah, that's the basic. We find some operation, something that's fixed in relation to what we want to glitch, and then we just wait a certain amount of time after that.
And would you also use a trial and error method? Just like gather lots of data, like wait.
Yeah, so exactly, yeah, that's one of the many parameters we need to optimize. So we have our trigger, we know when to start, and then we will start randomizing how long in time we wait before we glitch. And then from there, we'll see, oh, if we wait a long time, we have the desired effect. If we wait a short time, we don't. So we know that we want to optimize towards the longer times, like the longer wait times.
All right, yeah, thanks.
Thanks for the question. I think so. We're at time in terms of the official kind of end of the presentation. So if there's additional questions, I think maybe we can do that kind of after the talk. But I think for now we'll give another round of applause because this is amazing, and thank our speakers.